The next paper is entitled Probabilistic Planning for Continuous Dynamic System Under Bounded Risk. It is by Masahiro Ono, Brian Williams, and Lars Blackmore, and it's going to be presented by Brian Williams.
Great, thanks, Blake. So while a lot of the talks in this session are talking about doing probabilistic activity planning, in this what we're actually talking about is plan execution, right? But what we're doing is we're taking the results of a deterministic temporal plan, and then we need to execute it on a continuous world which is uncertain and incurs risk. So we're doing probabilistic planning, right, of a set of time-evolved goals, but the plan is going to be generating a control sequence. So you could also think of this as a form of model predictive control. I talked about part of this yesterday at a workshop. What I'm going to talk about here is the core algorithm. It's based on a journal paper. The only unfortunate thing is there's been about 10 years worth of work published in the controls community that kind of evolves to this. So I'm going to try to give you a short summary of that very quickly. My authors did a risk assessment and decided it was too risky to try to cover it all. So they left me to give the presentation. So the motivation that we have is that Boeing's been having us develop a personal air taxi. Right now, Google has their ground vehicle. Boeing wanted to get into the business, so they decided to say, let's make a robotic air taxi. In order to do this, we develop a capability where at the higher level, it's doing a temporal planning. In our case, it happens to be using a temporal plan network planner called Kirk. We then need to execute that plan. We do that with a navigator called Sulu. And then finally, if it's an oversubscribed problem, it becomes too risky, then you need to renegotiate your goals. And that's done by a system called Uhura, and that'll be described at ICAPS. Now, if you have these capabilities working together, then you get the following behavior. So let me just, hopefully the sound will work.
I want to go to the Boeing company.
Any more preferences?
I want to be there in 3 minutes.
Anything else?
I want to stop at Leisureland.
Any other requirements?
No.
We cannot get there in 3 minutes, but we can get there in 6 minutes.
That's fine.
Okay, there's renegotiating goals.
I have a valid plan.
So it did the temporal planning. Now it's navigating the vehicle.
There is a change in the weather condition. I will replan the path.
Okay, and then it flies the vehicle. So let me just talk about the planning component of that problem, right? So what we have is a temporal planner, which has basically done a travel plan, and the travel plan has been said, for example, that what I want to do is I want to go to Provincetown, right? From Provincetown to Bedford, I want to arrive there within 30 minutes. I want to go through a scenic region where I want to take to see whatever the scenic sites are there, that I am fuel conscious, so I want to minimize fuel consumption. So it is it's an optimal planning problem. And the probability of dying along the way, this is a kind of a region that's known for planes going down, should be very low. Okay, in that sense, it's a probabilistic planning problem. So more specifically, it's a form of time-evolved planning with time-evolved goals, but in particular, our problem is to execute a plan, but the plan has states that we want to achieve, such as being over Bedford or over the scenic region, as opposed to a set of executable actions. The second property is that the plan that we want to generate is an assignment to continuous control variables, right? The classic control problem, but where we're planning over some horizon. And then this is a form of probabilistic planning which is risk sensitive, meaning that we have a hard constraint on the probability of failure, and we want to meet that hard constraint. So what we want to do is to minimize fuel usage while guaranteeing that we handle that probability of failure, right? Okay, so what does the framework look like? Okay, so we're just going to talk about how we do planning as opposed to how do we planning and execution. I talked about the execution point yesterday. So if we just look at the planning problem, then we're first given a model, right, which is a set of stochastic linear differential equations. So we're not talking about discrete mode changes. We're just talking about assignments of continuous variables. We use a discrete time model. And then we have a set of exclusion constraints, which are the actuation constraints on the vehicles, and then the areas that we want to avoid. The inputs will be this temporal plan, which we refer to as a qualitative state plan, and then a set of constraints on the probability of success, which in the stochastic optimization community is referred to as a set of chance constraints. And then our output is both a schedule for start and end times of the plan, together with a control action sequence which respects the qualitative state plan and the dynamics of the vehicle. Okay. Now, we've developed a number of different variants of this planner, right? Today what I'm going to talk about is a version of this planner, not the planning execution whole loop, but a planner in which what we do is we reformulate this problem to an exact convex optimization problem, and then we solve it exactly. Yesterday I gave a different algorithm which was using an iterative approach, which at one level handles a more general set of problems, but it doesn't have the same hard guarantees in terms of convergence that this algorithm has. Okay? And then the combination of a qualitative state plan with chance constraints, we refer to it as a chance constrained qualitative state plan, or a CCQSP for short. Okay, so what does this qualitative chance constrained qualitative state plan look like? So it looks like a temporal plan, right? We have the start-in activity of being in Provincetown. We can remain in the scenic region. We can end in Bedford. And then we want to stay outside of the dangerous areas throughout that period of time. So those just like any set of temporal activities with simple temporal constraints relating them. In our case, the activities will have a set of state constraints which hold at the beginning of the time, through its duration, and during the end, and those constraints are over the continuous state variables of the system, and our state space is assumed to be continuous. Okay. In addition to that plan, we need to be able to specify the probability of success. So we specify that as a set of chance constraints. So we can take any bundle of a subset of these episodes and temporal constraints and specify a probability of success. So in this case, what we want to be able to say is that we want to be able to achieve our kind of vacation goals with a 99% probability of success, but the probability of dying is much, much lower, right? So the planner will then focus more on trying to guarantee safety than trying to guarantee that you're in the scenic region throughout the period specified. Okay. And then I already specified what our output is. So what the system will do is it'll come up with a schedule, which will schedule start and end times of each episodes, and then given that schedule, then it'll generate a control trajectory so that the state trajectory satisfies the QSP. Now, in order to do this, what we do is we build upon a planner that we developed back in 2005 called Sulu. And what we do is we take the qualitative state plan plus the dynamics, we re-encode that into a mixed integer linear program or a mixed logic linear program, and then we use that solver to solve the planning problem over a finite horizon. And these, as any kind of model predictive control problem, is of the following form, right? Where we have a cost function, which in our case is fuel usage, the set of equations which describe the dynamics from time t to t+1, so we've discretized time, and then a set of feasibility constraints that we have to satisfy at each point in time. And those constraints can vary over time. That's fine. We just simply time slice model. In those cases where we want to deal with things such as avoiding obstacles, which is a non-convex problem, then we can't frame it as a linear program. Instead, we frame it as a mixed integer linear program or a mixed logic linear program. And that would be the case here. Now, I won't have time to talk about how do you do the classical thing of re-encoding obstacles and dynamics, but let me just mention a little bit about encoding the qualitative state plan. So for each activity, right, we introduce a set of variables for start and end times of the simple temporal constraints, which is very easy within a set of linear constraints. For the set of episodes, we need to encode the start, during, or remaining and end constraints. So here's simply an example of encoding an end in episode. And here it says that at the end of the episode, which is event E, the constraint, the state constraint to stay in the region R has to be satisfied. Because we discretize time, our schedule may not exactly match up with the discretization. So we've basically said that we need to be able to satisfy that constraint within the time resolution of our time step, which is delta. And we do that, it's the same for the other episodes. Now, what this talk is about is how to deal with the stochastic problem. So in the case of the stochastic problem, we start with a deterministic problem, right? But we add in some noise. We'll add an additive noise here, which is a random variable, and we'll presume that that random variable is Gaussian distributed. Okay, so it's normally distributed. As soon as we add in that noise, then our state becomes a random variable, and we assume that those are Gaussian distributed as well, and we assume an initial Gaussian distributed state. Now, at this point, since our distribution is infinite, we can't guarantee any constraint with probability 1. So instead, we specify the probability that each constraint is satisfied, and that's referred to as a chance constraint. So here we're saying that the probability that we violate our constraints collectively is at most delta, okay? And that's the constraint that we need to respect. So we just have to solve that problem. We give it to a standard stochastic programming solver, and the only problem is that those things work terribly. So we did that, and we did it for a one-dimensional problem, which is to navigate the depth of a vehicle, and it works fine for that, but not for anything that scales much larger. So we focus most of our effort on how do you solve these stochastic programming problems. Okay? So, but before I go into solving that, this just shows you kind of the results of how the planner works. So I've run out of time. And so what you'll see is that in kind of the dotted line, that's a Sulu planner, which wasn't dealing with risk. What you'll see is that, that it will make good use of fuel, right? So you get 8.79 in terms of Sulu's use of fuel. But what you will see is that the probability of failure is about 94%. I don't know how many of you would be willing to take a vacation with that vehicle, but I certainly wouldn't. If you then look at the different cases where we put in different probabilities of success, then if we said that the mission success is only 90%, right, then what you'll see is that P Sulu came up with a plan which is 9.53, so that's within the bound that we specified. The algorithm is always guaranteed to be conservative, but it does use the risk that you provided, and it spends a little bit more fuel, so it uses one more unit of fuel. If we then reduce the probability of success to, or failure to 0.1, right, then we have a little additional cost, right, and it's able to come up with a trajectory which fits really closely within that bound, and then again, if you reduce the risk to 0.001. Okay, so as a user, you can just dial that risk. There are other algorithms which also are conservative, but they tend to be way too conservative, right? And so if there's a certain level of risk that you want to take, then you really want the algorithm to work to that risk, not to be overly conservative and pay a large additional cost. But you do want it to be conservative. Okay, so how do we develop the planner, right? So in the journal paper we presented, then it basically goes through a series of stages of problems. So we first look at the problem in which we don't have any, let me see if I, all the pointers. Let's see. Okay, so first we look at those problems in which the goals are all convex. So we need to stay within convex regions during different periods of time, but there's no convex regions. And in addition, we will assume that the time at which you need to be in those regions are fixed schedules. The next step that we did was that we said that we introduce obstacles and it becomes a non-convex problem, but a fixed schedule. And then the last step is that we then add in the temporal flexibility. And so we solve these as a series of increasingly more complex problems. I'm just going to talk to you about how to solve the first one, even though those algorithms are a little bit older. I think they're probably the most key for you to understand, and you can read the paper to understand the other algorithms. So the ideas in the first algorithm is going to be that we're going to do a risk allocation. So we're going to decide at every point in time where we're going to spend the risk for each point in time, and then for each point in time, how do we spend that risk for each individual constraint. For non-convex problems, we can choose one inequality constraint or another. So we'll select which of those disjunctive constraints we can apply the risk to. And then in the non-convex problem, the non-convex where we have flexibility in the schedule, then we'll do a branch and bound search over the set of possible schedules, right? And then for all those events that we fix, we'll then compute a relaxation and then reduce the problem to computing a bound using the previous two algorithms. But I'm just going to focus on this first problem. Okay, so the main thing I want you to then do is understand the idea of risk allocation during the remainder of this talk. Okay, so in order to do this, I'm going to use a race car example. Some of you have seen this before. So my problem is that I'm at the start. I want to go around the corner, cross the finish line, and I want to cross it as fast as possible. My problem is that I could plan a nominal trajectory, but we'll have some disturbance, like what you saw in the PTS example. So one way to do this because drivers really don't like to do probabilistic planning, is to simply design a safety margin, right? And then plan your nominal trajectory within that safety margin, so any deviation will push you off. And here's an example of a safety margin where we just stay away from the curb at the same distance. Not a particularly good strategy in terms of crossing the finish line. Instead, the strategy we could take is that we cut the corners. And if we cut the corners, then we can cross the finish line much faster than if we have a uniform margin. And the thing to note is that the area, the probability of failure is roughly the area, right, of that safety margin, and the area of those two different regions are the same. So there's a kind of an infinite space of possible safety margins that we can consider, as long as all of them take the same, all of them have an integral which is within the bound of risk that the user has specified. Our problem then is that what we're going to do is we're going to take an approach where we design a safety margin. We'll frame that as an optimization problem. Once we design the safety margin, then we'll reformulate the stochastic problem into a deterministic problem, and then we'll solve the deterministic problem. Okay. So I want you to both understand how do we do the risk allocation in this case, and then how do we do the reformulation. And those are my two remaining goals. Okay. And the one note here is is that the reason why cutting the corners worked well is that the path length was most sensitive to risk at the corner. So what we really want to do is to be able to allocate risk in those cases where it has the greatest sensitivity of the cost or gives us the greatest benefit. So our optimization problem is one of allocating risk, right, proportional to the benefit that you'll gain. Yesterday I gave an iterative method, as I said before. Right now we'll do is we'll reformulate the problem as a convex optimization problem where we're simultaneously designing the safety margin and then the continuous state trajectory of the system at the same time. So how do we do that, right? So first, the last slide in terms of intuitions. So in this case, what we'll do is we'll view risk as a resource, right? We'll then distribute the risk. So we'll take the risk, which is, for example, 10%, and then for each point in time, we'll decide how much risk that we're willing to take. And then for each time point, if there's multiple constraints, then we'll decide how to split that risk amongst the constraints. In these cases, the two obstacles, right? So we take 4%, which will be allocated here, and 3% are allocated to the obstacle on the left, and 1% is allocated to the right. And then these just simply have to add up to delta or less than delta. Now, how do we do that mathematically? And that's where I had this little thing which allows me to jump out of the slides if I'd run out of time. But I seem to be doing okay. So if you look at the formulation, right, then I gave you this stochastic optimization problem before, but I don't really like these random variables, and I really don't like this chance constraint. So what I'm going to try to do is to get rid of this chance constraint, okay? So the way that I do this is that the first thing is I'm going to make the assumption that delta is less than 0.5, and then at the end of this I'll exploit that assumption. But you'll just keep that in mind, is that we are limiting our approach to saying that if you want to take greater than 50% risk, then you're just too risky for us and go somewhere else. So I'm going to get rid of this joint chance constraint, which is over a conjunction of constraints. And the way that the reason I'm going to get rid of it is that evaluating that whether or not that chance constraint is satisfied involves a complex integral over a multivariate Gaussian, and that's very difficult to evaluate, and it's not something that you can deal with analytically. So what we'll do is we'll take that and we'll reformulate it to a set of chance constraints over individual inequality constraints, okay? And that becomes, which is over in essence, a univariate Gaussian distribution, okay? And then what we'll do is we'll take that univariate Gaussian distribution and reformulate it through designing a safety margin into a deterministic state constraint. So how do we do that? Okay, so the one assumption that we'll do is we use Boole's inequality, which is that we're going to say that the probability of A or B failing is bounded by the probability of A failing and the probability of B failing, and so we're just allowing the double counting of A and B simultaneously failing. If we do that, right, then what we can do is that we can distribute the conjunction, the chance constraint, through the conjunction, so we get the constraint that you see here, right? And then what we've done is we've introduced a lowercase delta, which is the risk of each individual constraint, and we've introduced an additional constraint which says that the sum of the individual risks that we take has to be within capital delta. Okay? Now the thing to note here is that the capital delta was a constant. The lowercase delta is a variable. We don't know it, so we need to be able to solve for that lowercase delta within our optimization problem. Okay? So here we'll take our problem that we had before. We'll distribute the conjunction or the chance constraint over the conjunction. We'll introduce lowercase delta in part of our optimization problem, and then we're ready to go. Except for we still don't like this chance constraint. We don't like stochastic optimization problems, so let's get rid of that last chance constraint. So the way that we're going to deal with that, right, is that we notice that, h of x is now a univariate Gaussian distribution. Okay, so if we draw that distribution, right, and we can take the mean of h of x, right, as a center here, right, then the closest that h of x could get to the constraint boundary g is a point at which the integral, right, on the right is equal to delta. Okay? So we can impose a constraint on the mean value of h of x to be the point at which the integral equals delta. And we can compute that function, and this is m of delta, and I'll defer for a moment what that m of delta is. What's nice is it's only a function of delta, it's not a function of any other variables, right? So given that, then we introduce a new deterministic constraint, right, which is the one that I've shown here, which is a constraint on the mean value of x, right, and it's introduced an offset, which is this delta. Now, the offset should be very familiar, right? Well, before I go into it, the m of delta just happens to be a little bit of a messy equation, right, which is the inverse of the CDF of the Gaussian, but we'll deal with that in a moment. But if we look at the interpretation of this, then the m of delta is basically our safety margin, right, and we replace the stochastic variable x with the mean variable of x, and so our optimization problem is designing the deterministic trajectory. Okay, so if I then look at this new problem, right, then here's the formulation that I have so far, right? So I now have a deterministic constraint. I've gotten rid of my stochastic variables. The one last thing I have to deal with is this nasty m. But if I reduce my probability of failure to be less than 0.5, then I get into a convex region of that inverse CDF, and I can frame this as a convex optimization problem. And so I just call the solver for that, and end of story. Okay, so I've given you the first stage of this process, and I gave you a high-level story of the next 3 stages of it. If you look at the performance of it, then it works very well on more complex kind of travel planning scenarios. And it also has been demonstrated on a range of other applications, including one of the authors, Lars, works at SpaceX on their robotic space tug, and so we've done a number of scenarios of docking with the International Space Station as well. Okay, so to just conclude, okay, so we've introduced as a new goal representation, right, which represents time-evolved goals in terms of a state plan, and then we've introduced chance constraints on it. We've introduced a stochastic continuous state planner for these problems, right, which are guaranteed to operate within user bounds on risk, but aren't overly conservative. We presented a stochastic solver, right, which will solve destructive linear programs, right, and you can use that for other applications. And finally, we've demonstrated SULU on PTS and on space, in the case of space, both in simulation and in hardware as well. Okay?